It's great to see you here at Ignite 2024 today in Chicago. My name is Tara.
And I'm Estefani.
And we're both product managers on Azure Cosmos DB.
Okay, how many of you in the audience today have heard or used Cosmos DB before? Okay, almost everyone here. Great. But for those of you who don't already know, Cosmos DB is Azure's fast NoSQL database. So fast that customers like OpenAI use us as their database service. And for today's demo, we're going to focus primarily on the NoSQL API.
So we know how easy it is to get lost when you're starting off on Cosmos DB and building your application. In today's session, we'll differentiate what's important between getting right before you build your application and what you can still optimize after building your app. So the two things that we want to focus on before building out your application are how to data model your app, as well as choose a good partition key. It's really important to get these two things early on correctly, because refactoring your data model or changing your partition key can actually lead to refactoring your application's code, which we all know takes a lot of effort and time to do. We'll be walking through how to do that with a sample application, and then we'll go over best practices and how you can monitor and troubleshoot performance after building your app as well. So with that, Steph, do you want to tell the audience what we're building today?
Yes, so Tara and I have decided to join forces, and we're going to have a small startup where we're going to be selling products such as t-shirts, mugs, and other products where you have your face on it. And the reason why we did this is we want to make sure our friends and family can have us just as an arm's length reach.
And while we build our application, we really want to take a step back and understand what we want our users to do. So the first thing is that we want our customers to be able to view our product offerings on the app. We're offering 3 products for them to choose from, which are mugs, shirts, or stickers. We also want customers to be able to search for products in our catalog, place an order, and when they log back onto the application, they should be able to see all their past orders as well as all the products that they've bought.
Okay, so Tara, can you show us what this might look like in Cosmos DB?
Yeah, let's do it. So I'm going to go over here to my portal, and you'll see that I have a couple containers that are set up already. The first one is called product details. Within this container, you'll see that I have an entry for all of our different product offerings. So like I said before, we're offering stickers, and we have data on what the price is, the quantity, description, as well as things like the t-shirt and the mug. Besides that, we also want to make sure that we're tracking all of our user details. So the customers that are actually on our application, we're keeping track of things like their user ID, their name, their address, as well as their email.
Okay, should we also have somewhere where we're tracking the orders and the users and the relationship between the products as well?
Yeah, we definitely need another container to track all of our user orders. And there's 2 ways that I've been thinking about modeling this data. The 2 ways we can do it are either through referencing or embedding. Referencing is when you store only a reference to the related data. So in this case, we would have our order documents, and to get the products that the customers ordered, we would store something like a product ID. Embedding is when we're actually placing all of the related document information, so all of those product details, into our order documents. So to put this more clearly, as you can see here, the containers on my left have the referencing modeling, where we have our new container called user orders, and we have a reference to the product ID within these order containers, or order documents. And you'll see here that we have this product ID, but we don't have any details on what exactly that name of the product is or the cost of that product. We're getting that by referencing to another container, which is our product details container, to get all of that rich detail of what the customer actually bought. The other approach is embedding. So you'll see on the right that one approach of how I've embedded this is just simply putting all those product details into the order documents itself. So to get the full picture of what the customer has ordered, we only have to do one call to that container.
Tara, I have a question. Wouldn't we kind of have an unbounded array problem if we have all of the products nested into the same container?
Yeah, that's definitely a risk with embedding. So we want to give these guidelines for when you should reference versus when you should embed. You should definitely reference when you have a one-to-many relationship with the properties in your document. So like you said, if you have an unbounded relationship where a customer can potentially buy multiple products in their order, the risk of embedding in that scenario is that the product can get too big. The document can get too big, and you can run into that 2 MB doc size limit. But in our scenario, since we are a smaller shop, we can say, like, let's put a limitation on how many products a customer can buy, and only let them buy less than 5 products.
Yeah, that's a good idea.
In that scenario, embedding might be a good approach for us because we have a one-to-few relationship with the order and the products that a customer is choosing. We're also going to be frequently querying for the orders and products together, and this is another scenario where embedding works.
Are there different ways to kind of do embedding? So I'm curious, because NoSQL is so flexible in terms of how we model our data, are there kind of other ways we can embed?
Yeah, so we saw one approach where we were embedding all of the products into the order documents itself, but another way we can think about that is approach one, as you can see here, where we have separate documents for each of the products that a customer has bought. And what this means is that for each unique product, we would store all of that information in a separate document, and all of these different products would share the same order ID if they're in the same order. So to put that more clearly, as you'll see here, in approach one, we have multiple documents for each unique product a customer has bought, and we're embedding the order details like the order ID and the order date as the same property across these documents. In approach two, like we saw earlier, we just have one document per order ID, and all of the product details are embedded in there.
Okay, so from what we're hearing, maybe approach two might be a better approach. We have everything nested in one document, and I think we're going to be typically querying by documents and getting all the orders and all the products in that particular document. So I think maybe this approach might be better for our solution.
Yeah, one thing I want to point out is that when a customer is looking up their orders, they also want to see what the total cost of their order is. So in approach one, we would have to sum over all of the individual costs of the product to get the entire cost for the order, but in approach two, we can simply just look up the total cost since all the products are within that order document.
All right, maybe enough with the theory. Can we get to see it in the portal?
Yeah, let's do it. All right, so I'm gonna go ahead and open my my Data Explorer again, and you'll see that we have our nested products and orders data model, and the documents look like what we saw earlier. And I'm gonna go ahead and run this query. So we're frequently going to just want, based off of the user ID, get all of their orders, and you'll see that when I specify this, I'm just getting one document which has all of their product details, and we just get that total cost that's summed up at the bottom here.
Awesome. And I see you just went to the query stats page. The request charge is 14 RUs. What is an RU?
Yeah, that's a really good question that a lot of folks on Cosmos DB have. So an RU on Cosmos DB, for any operation that you do, whether that's a write or a read or a query, it costs you a request unit. And so a request unit is an abstraction of the cost of a request in terms of CPU, memory, and I/O, and it can either be provisioned at the database or container level. You can also change your performance programmatically, but in this case, request units per second when you provision means that at any second, all of your requests can burst up to the amount of RUs that you've provisioned per second.
Okay, so for our query we just ran, that was 14 RUs. It seems a bit excessive. Can you give me a sense of how much a typical 1 KB doc for a read or write would kind of cost for us?
Yeah, so for reference, 1 KB read on Cosmos DB costs 1 RU, and a 1 write of a 1 KB document costs 5 RUs. Query charges depends on the complexity of the query as well as the documents involved, and indexing can also impact your RU charge, which we'll touch on later.
Gotcha. When we think about this, wouldn't partitioning also make a difference here?
Yeah, do you know what partitioning is?
I have some idea, but can you explain to me what it is?
Yeah, so partitioning is a really important concept on Cosmos DB, as it actually is what allows you to distribute your data horizontally based off of your partition key. So if you come from the relational world or a SQL background, you might know that to scale your database, you buy more cores and CPU to scale vertically. But on Cosmos DB, it'll automatically distribute your data horizontally with partitioning, and that partition key that you choose is instrumental in doing this behavior. So So to put this more clearly, you can treat this diagram as a Cosmos DB container. And in that, you'll see that we have these big rectangles, and you can think of these as your physical partitions. So these are actual physical servers that hold your data on Cosmos DB. Within that, we have smaller containers, and we can call these our logical partitions. So when we're thinking about, okay, how are our logical partitions organized, this is all dependent on that partition key that you use. So in this case, we're partitioning by order ID, and you see that we have a document that's coming in where the partition key value is order 123. So Cosmos DB will hash over this partition key value to tell us where exactly in our logical and physical partitions it's going to. So you'll see we have multiple logical partitions mapped to a physical partition, and if you pick a partition key that doesn't have a high cardinality, like let's say order type, and we're getting a lot of orders from one, that has one specific order ID, you can see that we would just be hitting that one physical partition because we're always hitting that logical partition. There are some limitations when it comes to physical partitions and logical partitions as well. So like I said before, you always provision a request units per second on your billable resource. So you'll see here that we are provisioning around 50,000 RUs on this container. And what Cosmos DB does once you tell us the performance that you're provisioning is that we automatically set up your physical partitions based off of the performance that you provision. So each physical partition can go up to 10,000 RUs, and this leaves us with 5 physical partitions. And each physical partition can hold up to 50 GB of data. Once you surpass that 50 GB limit, Cosmos DB will automatically split those physical partitions and create more for you. Within the physical partitions, like I said, we have logical partitions as well, and each logical partition can hold up to 20 GB of data. So this means that for each value of your partition key, so like we saw before, order 123 is an order ID, that order ID specifically can hold up to 20 GB of data. If you anticipate that that value can surpass 20 GB, like you anticipate that some order IDs will have more than 20 GB of data, you can actually use a feature called hierarchical partition keys, which we'll also touch on later, that can help you add more levels to your partition key and surpass that 20 GB limit.
Okay, so partitioning seems like a very important concept in Cosmos DB. Can we talk about what our partition key was for the container we just created?
Yeah, so that partition key was order ID. So let's zoom out and kind of understand what our data access patterns are to figure out if that was a good partition key overall. So the two things that we anticipate our customers doing on our application for this container is they're doing a lot of orders. So that means we're going to have multiple write operations per order into this container. We're also going to query for all orders by user ID. So for every user that logs into our application, we're going to pull up all of their orders. So as you can see, we're writing a lot of orders, and we're also querying for those orders.
Okay, awesome. So would order ID be a good option for us?
Let's double check. So we saw that that query was 14 RUs, which doesn't sound too expensive, but we can anticipate lots of orders coming in every minute, so that can easily add up. So I've gone ahead and tried to test out another high cardinality property like user ID to see if that might be a better partition key for us. So I have two containers here, one that is partitioned by order ID and the other one that is partitioned by user ID. And I'm going to go ahead and run this query to get all of the orders where user ID is this one. So I'm going to go ahead and run this query. And you'll see here that we have this one document that shows up, and the RU charge was that 14 RUs. Let's go ahead and run the same query on a new container, which is partitioned by user ID instead. And it has all the same documents. The only change is that partition key. So you'll see here in query stats, it's only around 3 RUs. Do you have any guesses on why that must have been the case?
I'm thinking that has to do with the partitions.
So like I said, in the first container, we were partitioned by order ID. We can actually go in here and look at the per partition query metrics. So if I go back here, I can download this, and I already have it here. I'm going to open it up, and you'll see that for each physical partition, we had to visit around 5 physical partitions that we had to get that retrieved document. And that's because we were partitioning by order ID. So in order to find a specific user ID, which our query specified, it had to visit all of those 5 partitions. And on Cosmos DB, we call this a cross-partition query, and we get that fan-out charge of 2 to 3 RUs for each physical partition that we have to visit.
Okay, that makes sense. That's why it's 14 RUs.
Yeah. For the second query where we partitioned by user ID, I'm going to go ahead and download those metrics and open it. And you'll see here, we only had to visit that one physical partition since we specified the user ID and we were also partitioning by user ID. So we avoided that fan-out charge.
But 14 RUs to 3 RUs is actually not that big of a deal, really, right?
It's not that big of a deal, but when we are doing these requests around thousands of times per second, that 14 RU difference between 3 RUs can actually decrease our RU charge and our overall cost on Cosmos DB by a lot.
Great.
Cool.
Another thing I learned about recently was some of the provisioning models on Cosmos DB. I think we are using autoscale, which allows Cosmos DB to scale us up or down depending on our utilization. So we as a customer don't really have to worry too much about provisioning it at the right amount because Cosmos DB will do that for us. What I did learn was I'm concerned about the pricing. I think we are charged 100% of the max utilization per partition, even if some of our partitions are not active all the time. Is that right?
You know what, I was actually worried about this too, but I was reading about new updates in Cosmos DB, and it turns out we have this new feature called dynamic scaling, which can actually help us in this scenario. So for everyone that doesn't know, previously on autoscale with Cosmos DB, all of your partitions were scaled up based off of your most active partition in your most active region. This works well for uniform workloads, but you can see here where workloads have one active partition and some other idle partitions or partitions that aren't all uniform, as well as regions that aren't as active as other regions, you are still scaled based off of that most active one. So this can really hurt your cost on Cosmos DB in the past. But luckily today with dynamic scaling, you are now charged for the consumption of all of your partitions across all of your regions, which is much friendlier in this scenario.
That is awesome. So does that mean that we don't have to worry too much about partitioning now?
Not exactly. Even though this helps you save on cost, this can also still hurt your performance. So it's really important to still do the partitioning best practices in this scenario. So as a recap, you want to make sure that your partition key has high cardinality. And if you are using a hierarchical partition key, that top level has high cardinality as well. And you want to make sure you're choosing a key that will spread your RU consumption and data storage across your logical partitions evenly. You also want to make sure that if you are a write-heavy workload, again, choosing a high cardinality partition key is really important to use your RUs efficiently. And for read-heavy workloads, so in our case, since we are often querying by user ID, using a partition key that you're often querying by is really important as well, which is why we decided to go with user ID as our PK.
Okay, lots of stuff. Can you recap me what our data model looks like in the portal?
Yeah, so let me go back to the portal, and you'll see here that we have our final orders container. What we have so far is that we're nesting all of the products within our order documents, and we're also partitioning by user ID. Just to recap, we also had those 2 containers that keep track of our product details as well as our user details. And user details is also partitioned by user ID.
Okay, so it looks like we have 2 containers partitioned with the same partition key, which is user ID, I believe. Would it make sense to do something called co-location, where we basically just have one container partitioned by the same partition key, and then add in the 2 different types of document into that same container?
I didn't know you could add different documents with different schemas on Cosmos DB. What's co-location?
Yeah, Cosmos DB, again, is super powerful, right? It's not like a relational database, right? We can actually join different products by adding the different, something called a property type into the same document. So Cosmos DB is schema agnostic. So you might think, oh, we can't actually add the 2 different business logic into the same container. But in Cosmos DB, it's actually considered a good practice to do so if you typically query for those things together. So let me walk you through in the portal how that would look like. Okay, so this is an example of a query where we have specified the order ID, and I've labeled in the document something called the document type, which in our case is going to be an order. I also have the same query is also looking for a user ID, and the document type is called user. So both of these same documents live in the same container. And so when we query this, we can actually create a join, an artificial join across those two data containers. And so you can see here my order documents as well as my type user document as well.
Okay, this makes sense. I assume that we want to do this when we want like the shipping information for a user to show up when they are looking at their orders, to see where their orders are going to. So rather than co-locating both of this data into this container, what if we just add a property into our container which keeps track of that shipping address? So like this, where we have shipping address here, and we can just get everything with just one call and a more simple query.
Yeah, I agree. I think adding everything, embedding that property also into the document would also work well for our use case.
Okay, cool. I think this is looking good as our final orders container. What do you think?
I think so. I think we are now open for business.
Awesome.
Great job. All right.
All right. 1 month later. Hey, Steph, it's nice to see you a month later. I was actually looking at our reviews, and it looks like we're getting a lot of 1-star reviews that customers are complaining that doing any orders are taking them a really long time.
Oh no, our sales. Okay, do not fret, we can solve this. So Cosmos DB actually has a lot of observability to try to diagnose what's wrong with our application. And sometimes when diagnosing, it can be kind of daunting to detect what's wrong. So when you issue a request, the request lifecycle it's really endless, honestly. There's different steps at which something can go wrong. And typically we have 2 different categories. One is on the client side, the other is on the server side, right? So the client side is everything that happens before the request gets to Cosmos DB. And so those are things like maybe you have your app on a VM, right? So maybe there's something wrong on your VM, or you have some Kubernetes, maybe there's something wrong on your network, right? Maybe you made a recent app change and kind of made everything slower than you expected, right? Those are all the client-side type of metrics. And so we actually have something called client-side diagnostics that will show you in just a second on how to use that feature to detect if there's something wrong on the client before you try to diagnose on the server. Secondly, we also have the server-side diagnostics, right? So once you identify that there's nothing wrong on the client side, you can then look at the server side. And for the server side, we have a couple of different ways to monitor this. One is via metrics. Metrics are near real-time time series data. And these, because they're so near real-time, they're actually really great for alerting. So you can tell us, hey, my utilization is kind of going to 90, 100%. Can you alert me that there's something going wrong here? And those are really good use cases for that. Next, we also have logs. Logs are very fine-grained traces that are ideal for really debugging the root cause of an issue. So maybe there was something wrong with the query. You can use our logs to go deeper and try to understand where did it go wrong. Okay.
Okay, that makes sense. I think we should start with the client-side diagnostics to rule out if anything went wrong there.
All right, let me set that up for us. Okay, so in our app, I've enabled the client telemetry. It's a very simple flag where you set disable distributed tracing to false, which is a double negative. But once we enable that, we can do a simple console output of what those logs are doing. So here we have, in our terminal, the JSON document. So I'm going to go ahead and copy this over to JSON and do a simple prettifier on the data. And here we have a really long JSON of a lot of different metrics. And I'll walk you through it because, again, it can be a little bit daunting. I'll walk you through the main things that we should try to debug on our app. All right, first things first, we see that there is a 408.
No. What does that mean?
A 408 is a timeout issue. And this is not great. So let's take a look at why this could happen. So we are doing a simple create operation, and the duration is 1.2 seconds. That is kind of abnormal for it to be that long, because this is, again, Cosmos DB, very fast database. So let's try to debug. I think that something that could be wrong during these cases is maybe we don't have enough CPU. So let me quickly search here for CPU and see what we have.
99%.
Okay. right? That shouldn't be there. So typically, we want to keep it to closer to around 40%. And sometimes when we try to debug, it could be many different issues, reasons why this could be an issue. Maybe you are running a lot of cross-partition queries, and it's taking a lot of resources to go and travel to each partition to access the data. And sometimes, like in our case, we didn't really know what we were doing when we were starting up, and we didn't provision enough compute on our VM to run this application. So how about we go ahead and change that, and then see how it's actually doing in a little bit.
Okay, sounds good. It also looks like this is just showing us the details for one request. Is there a way where we can look at scale all of the requests that are going on?
Yeah, great question. I've actually set up our OpenTelemetry so that we can actually send over data to our App Insights cluster. And OpenTelemetry is an open source way to, basically an open source framework where you can export data to one of your data export locations. So it can be, it's tool agnostic, so it can be really any data source of your choice. Hence the name OpenTelemetry. And so here we have in our App Insights cluster, a couple different instances of my app. So I'll go directly into one of them to try to debug if there's any additional issues on the client side. Just quickly looking at the logs, I do see that it is already sorting by duration, and my longest duration operation is the create database, if not async operation, which I can kind of already know why this is an issue. Let's try to investigate a little bit deeper about why this is happening. So scrolling down to the operation, this gives us a time chart of every single step. Here we go. Every single step of the process of the request lifecycle and where it kind of had latency. So in our case, most of the latency actually happened on this step, and the rest of the latency is pretty normal, as you might expect. And that's because, again, we were doing this create database operation async, which is not really best practice to do, actually. So typically, when we do this create database async operation, it's doing a lot of unnecessary metadata calls, especially on the hop path. So instead of doing this create database async operation, how about we just do a get database async, a get database operation, which if we can see here is actually a lot faster, only 351 milliseconds. So I think that kind of resolves some of our latency issues on the client side.
Okay, got it. So it looks like we resolved everything on the client side, but now I'm getting a little worried that something might be up on the server side as well. We didn't really look at all of our different query patterns, but maybe there's some place where we can optimize even further there.
Okay, so here I have in our log analytics a query that kind of detects for every collection if a request charge is greater than 200, which is also very expensive. I want to see all the queries that are very expensive. So in our case, this query was 233 RUs. And let's take a bit of a closer look to see if we can optimize this query. So let's copy this and paste this over to our VS Code. Actually, we have a new extension in VS Code where you don't actually have to leave your IDE to access Azure. And so here you can select your Cosmos DB account and drill down to your collection and open a query editor view. So let's go into here. And when we run the query, we can see, yes, it is 223 RUs, which is kind of excessive for simple kind of search query. And then if we scroll down here, we're seeing some recommendations on indexing.
Okay, I've actually never heard of indexing on Cosmos DB. Can you give me a little crash course on what that is?
Yes. So indexes are a really cool data structure on Cosmos DB. So it's basically when you create a JSON document on Cosmos DB, we convert that into an inverted index, which allows the data retrieval and lookup of that document to be a lot faster, instead of Cosmos DB having to scan every single document. So how that works is that by default, Cosmos DB indexes every single property of that document. So you can see on the left-hand side, we have the property paths of that document as well as the values. And when we perform a lookup of that query, so in our case, we are querying for all documents that contain Springfield, we can easily do an O of 1 lookup with an index seek operation. Okay, to put it in simpler terms, it's as if we have a book, and I tell Tara, hey, can you actually look up every single page where it contains Springfield? it's going to take her a month to actually go through every single line item, right? But what if, while I'm writing the book, I actually create an index and I say and I create a term of where it exists in the book. Then I ask Tara the same question, and she's able to actually execute that query a lot faster. And that's exactly what Cosmos DB does under the hood.
Got it. Okay, so I understand that indexing can help us when we're querying and when we're reading documents, but let's say we have a document that has like 100 properties, and I know Cosmos DB will default index every property in that document. Can't this get really expensive if we're a really write-heavy scenario because Cosmos DB has to index everything?
Yeah, there's definitely a trade-off here. So when we think about indexing every single property, this is ideal for a lot of lookups, a lot of queries, and this is essentially a read-heavy workload. It actually makes the lookup a lot faster and improves the query performance. However, if you have a write-heavy workload, indexing every single path is not ideal because, again, it can get expensive and you're not doing a lot of reads. So we actually recommend for write-heavy workload to update the indexing policy to exclude everything and just include the things that you typically query for.
Got it. Okay. So I was also wondering, in our query, we are not only looking for the shipping address, but we're also adding another filter of like time as well. So how does indexing work when you have 2 or more filters?
Yeah, so what happens when we have to query 2 or more things is that first the query engine looks up the first property or the first filter in the query, which is Springfield, and then retrieves all of the documents that have that property. Then it does a second lookup. In our case, we're doing a range filter, so it looks up all the documents that are greater than 11/14 or November 14th, and then it retrieves all of those documents. And then finally, it does an intersect operation, similar to a join, which basically retrieves all the documents that have both of those filters in it.
Got it. Okay, I also saw when we were looking at our index metrics that Cosmos DB was suggesting a composite index. What is that?
Yeah, so composite indexes are something that we can add to our indexing policy. And indexing policy is just a way for the query engine to know how they should index your document as you insert it. In our case, we can actually add a composite index, which makes it easier to retrieve documents where you query 2 or more things together. So if we have that query where we're looking for shipping address city equals Springfield and also order date greater than 11/14, we can create a composite index that actually concatenates sort of those 2 values together. And when we do a lookup, it's a lot faster than having to do the 2 lookup operations for the separate properties and then the intersect operation. So it removes all of that logic and just has 1 lookup to that particular document.
Okay, makes sense. How do we actually go ahead and add this to our workload?
Yeah, it's actually pretty simple. Let me walk you through an example in the portal of how it's done. So this is our existing indexing policy. It currently, again, indexes everything in the portal. And then I've created another container where I've added our composite indexes that was recommended by our VX Code indexing metrics. So I've added a composite index for shipping address, state, and also the order timestamp. Now let's go back and try to run the query again to see if it changed anything. Okay, so when we run the query, we see now that the query is 41 RUs, which is a lot more efficient.
Yeah, so as a reminder, when we were running this without any indexing, or when it was default, without the composite index, it was charging us around 220 RUs. So this is a pretty big difference. So thanks, Steph.
Great, nice job.
All right, I do have one more question, though. I want to look up users based off of their email, and customers on our application, some of them might capitalize the first letter of their email, or they might do in all caps. So I was just simply doing this contains query to look up this email, and I set the insensitivity to true, but when I ran the query, it was like around 1,000 RUs. You want to take a look and try to help me out here?
Yeah, let's go kind of try to figure out if we can optimize this in some way. So when we run this query, yeah, you're right, it is 1,000 RUs. And actually, the latency of the index lookup is also very high as well. So let's do a simple change here. So instead of using contains, let's just do starts with. And let's run the query again. And now it's 27 RUs.
That's crazy that just changing the operator could lower the RU charge by that much. Can you walk me through why that was the case?
Yes. So what's actually happening is that under a hood, when we perform a contains operation, we're doing a full index scan, right? And what that means is that we were discussing all the property paths. So we take the user email property path, and then we retrieve all the documents that have user email. Then we run a contains operator on those values, and then again retrieve those documents that have 𝗦𝗲𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀𝗀 operation, if you have a property value like user email, which has high cardinality meaning a lot of distinct values. So user email has a lot of distinct values, right? That means that the lookup time is going to be O of n, right? Because it's going through every single value. However, if we do a simple change, which was the starts with operator, now instead of having to go through every single document for user email, we can now do a scan a subset of that document. So instead of having to scan the entire user emails list, we just scan things that start with 𝗏, right? And that makes it still O of n, but some subset smaller than the original query. And that's how come we've been able to optimize that.
Okay, I was trying to investigate this further to make it even better, and I saw something that there's like a computed properties feature in Data Explorer that we could use. Do you know anything about that?
Yes, so again, this is Cosmos DB, and we can do even better than 27 RUs. We can do this with the help of something called computed properties, where it essentially is a derived property that allows you to create a new property from your existing properties. The way we do this, simple change in the portal or SDK, you create the name of that new property, and then you select your query logic. Finally, once you do that, you can add in an index so that we can then make the query a lot faster. Okay, let me show you how we can do that in the portal. All right, so here I've set up my computed properties. And again, the reason why this query was so expensive and also very slow is because we'd have to scan every single property in that particular user email path. So what we want to do is try to make this as close to an index seek operation as we can. So in our case, we can create the query logic where we're just lowering all of the user emails to something that's case, so it can be a case sensitive sort of search and make it a lot faster. We add the computed properties here, and then we can simply go to the indexing policy and add it again as a new included paths. And once we do this, let's go ahead and check in our VS Code again and see how much more efficient it can make it.
Got it. So Cosmos DB default indexes everything, but if we use computed properties, we still need to specify that in our policy, right?
That's right.
Got it.
So yeah, so if we run this, now it's even more efficient. So it's 14 RUs now instead of the 1,000 RUs that we started with.
Well, thanks so much for helping me debug this.
Nice.
All right, 1 year later. Hey, Steph. Business has been booming and it looks really good, but I'm getting a little worried because I was looking at our insights and it looked like one physical partition had around 100% usage. Can we figure out what's going on with that?
Yeah, so let me walk you through some of our metrics that we have today and see maybe what could be going wrong here. So in our normalized RU consumption, we can see that around this time where we had a couple hours, we saw that consumption spiked up to 100%. And this inherently isn't bad in itself, right? Oftentimes we might get scared if we see 100% utilization. That in itself is not bad. It could just mean that we're actually using all of the RUs efficiently as we can. This can be alarming if you also have 429s or throttles along with sustained period of high utilization. But in our case, it looks like it just spiked and then it kind of went down. Okay, but let's keep taking a look at maybe what could be causing some of this skewness. And if we look here, we see if we split our normalized RU consumption metric by physical partition, we can see that one physical partition range 0, is actually more active than the rest of my other 4 partitions. And I think we should take a deeper look and see if maybe there's something wrong here, right? We want to prevent any issues in the future.
Yeah, so as we saw before, multiple logical partitions map to a physical partition, and and we partitioned by user ID. So is there any way we can see if like one specific user is getting writing multiple requests compared to the other ones? Because that might mean that we're only hitting one physical partition.
Yes. So we actually have a log analytics table where we can see the partition key consumption across the logical partitions. So in our case, I've written this query, and I can see the physical partitions as well as the logical partitions associated with it. And here we can see that I've sorted it by request charge, so highest RU charge. In our case, we can see that most of the request charges coming to that one physical partition ID 0 are actually coming from just the same partition key. And that partition key is this DD, and if you remember correctly, we actually partitioned our container by user ID. So this is maps to one of our users, right? Let's take a look. I think this is sort of abnormal behavior because one user shouldn't have to spike that much. It doesn't make sense. They're just making orders, right? So let's take a look at why this could be happening. So let's copy this user ID over and try to, sorry about that, try to filter it to that. All right, so when we run this query on user ID, let's view this in JSON. It's actually mapped to one user, username 𝗦𝗲𝗀𝗀𝗶𝗵𝗀. Do you know who that is?
Okay, this is someone I know from college. It seems like she's buying a lot of our products, but then she's reselling it at a higher price. So
what?
How do we stop this from happening?
This can't be. Okay, let's take a look and try to figure out how we can resolve this issue.
All right, the first thing that comes to mind is, can we implement some type of cache so when we're constantly looking up this user, the performance is better?
Yeah, so caching is really good for lots of repeated read scenarios. So if you can imagine, like maybe a very popular product during the holidays would benefit a lot from caching, but in our case, we're doing a lot of writes as well on the order. So caching is not really gonna resolve that issue.
Okay, I read something about client backoff policies. Can that help us delay these requests?
Yeah, so client backoffs essentially work well when we have the SDK waits a little bit of time before they actually retry the request. And in our case, this might help temporarily, right? It's gonna eliminate the bloat temporarily, but because this is one of your friends who's reselling our products, I don't think it's actually gonna help in the long term.
Okay, well, is there any way we can just limit the number of operations that they can do?
Yeah, if we actually don't want them to continue making requests on Cosmos DB, what actually happens behind the scenes is if this particular customer is close to reaching our 20 GB limit per logical partition, which it looks like they're on track to reach as well, Cosmos DB, the service, will actually allow them to make any more requests. And so they'll be left high and dry.
Okay, honestly, when I was looking at our sales, it looks like business is booming just because of 𝗦𝗲𝗀. So how do we go past this 20 GB limit and just let her buy as much as she wants to?
Well, let's ask the audience. Do you guys think we should let her continue using our product to resell it? Yes? Okay, yeah, we'll take it. The way we can actually enable the sales is by using our feature called hierarchical partitioning, where hierarchical partitioning can allow us to configure up to 3 levels of hierarchy. And what that can do is actually expand the 20 GB limit to even greater than that. So let's go into the portal to show you how that can easily be done.
I heard changing a partition key, though, is really hard on Cosmos DB. Isn't this going to involve a lot of work for us?
No, actually, this is actually pretty simple now in the portal. We have under scale and settings, easily accessible way to change your partition key. You just select change here, you select your new container, and then this is where you can define your new partition key. Additionally, here is where you can select the second level of hierarchy for your partition. But before we actually change anything, can we go back to our data model to try to decide on what would be a better fit for the secondary hierarchy for the partitions?
Yeah, so our first key is user ID, and as we know, one user is very close to reaching that 20 GB limit. So adding that second level of something that also has high cardinality and is also something that we might be querying by, like order ID, could be really useful in this case. What do you think?
Yeah, I think that because order ID also has lots of distinct values, I think adding that as a second hierarchy would actually help in this scenario to expand 𝗦𝗲𝗀𝗀𝗀's usage from that 20 GB limit to an unbounded amount until she maybe reaches that amount.
Got it. And yeah, we can always also add a third level of ID to make sure that we never run into that 20 GB limit as well.
Okay. All right, so thank you so much for joining us today. We walked you through the entire app cycle for developing on Cosmos DB. So you were able to learn everything that you needed to know before building the app. So that is how to best model your data on Cosmos DB, how to choose a really good partition key and what happens if you don't, and then everything that happens after you build the app, right? We saw everything like slow requests, how to optimize your queries, and we were able to resolve some of those issues. So thank you for joining us. We are now open for questions. And also we have some resources here, and we have someone from PeerSpot outside if you want to leave Cosmos DB a review.
Thank you.
My question is the dynamic autoscaling that you showed versus the autoscaling. I just wasn't clear, is that like a totally new thing, or is it dynamic autoscaling is just built into the autoscaling feature?
Yeah, so it is the new autoscale behavior, but you still have to opt into it for your existing accounts. So if you go into the portal under features, you'll be able to turn it on, and once you turn it on, it'll automatically apply to any of your autoscale containers.
Awesome.
Yeah.
Thank you. And thanks for all the info. That was awesome.
Thanks.
Thank you.
Cool.
Okay, we'll be here if you have any questions.
Yeah, thank you guys.